Now let's check. Are these parallel? So V1 parallel to V2? Question? Well, are they scalar multiples? No, they're not scalar multiples. The only way you could turn this 1 into a 2 is if you double it. But if you double 3, you don't get 1. So this is not going to work. So no. That obvious? How else could you check? That careful. Oh, that wasn't you? Cross product. So you got to go back and look. Last class, what were we, 10-4? Let's see if I can find it here. It was one of those theorems. Here we go. Two non-zero vectors u and v are parallel if and only if the cross product is 0. But cross products suck, don't they? I mean, computing cross products by hand. So I think it's easier to just look and see that they're not scalar multiples. But you could use that. Is not the 0 vector. Okay, so they're not parallel. What about perpendicular? V1, perpendicular. So hold on, hold your horses for a second because I'm going to call on somebody now. So there's some people I don't know. Let's see. We'll start in the back there. Kieran? Who's that gentleman next to you? Have you met him before? No? What's your name? Jaime. How are we going to check to see if two vectors are perpendicular? It's all right. If you don't know, it's okay. If you say, no, I'm not quite sure, that's okay. Not sure. Okay, so I'll open it up to the table. Except Kieran, you're not allowed. If the dot product is what? 0, they're perpendicular, right? Okay, so let me take dot product. I'm going to take V1 dot V2. What is that? So let's see. Multiply 2 plus 3, then what? Minus 4, this is not 0. What does that mean? Are they perpendicular? No. All right. I'm trying to show their skew, so they better not be parallel. They better not be orthogonal. So far, so good. The last thing I have to show is that they don't hit each other. Just got to make sure that they don't intersect. So what would it mean for them to intersect? Let's see. We'll move over to this table. If these two lines intersected, anyone at that table, and then, sir, what was your name? In the backpack? You, sir. Yes, you. What was your name? I'm not calling on you. I'm just asking for your name. Okay. All right. So anyone on the table, what would have to happen if two lines intersected? They would have to have at least one point in common, right? One point in common. Right? They would have to have one point in common. What that would mean is that at some point in time, let's say, this x component and this x component would have to be the same. And at the same point in time, this y component and this y component would have to be the same. And this z and z component would have to be the same. So the question is, does there exist a t and an s such that the following is true? 1 plus t equals 2s. Negative 2 plus 3t equals 3 plus s. And 4 minus t equals negative 3 plus 4s. See, are you going to be able to find a t and an s that make this true at the same time this is true, at the same time this is true? Do you agree then that x, y, and z components would match? Yeah? What does this look like to you? System of linear equations. You actually have 3 equations and 2 unknown variables, yes? So there's various ways to solve this. What I'm going to do is move all my variables to one side and leave constants on the other side. So let's take a look at that first one. I guess I'll leave the t on the left. I'll bring the 2s over. I'll take the 1 to the other side. On this one, I'm going to leave the 3t on the left. Bring the s over. Y'all double check me here. Take the negative 2 to the other side. That look right? And the last one, negative t. And then bring the s over minus 4s. And then negative 7. Y'all double check me there. That look right? Okay. Here's my system of equations. Now, what we'd usually use at this point is some version of Gaussian elimination to do this by hand, or yep, that's basically elimination. You're taking one equation and then doing something with the other one, right? There's various ways to do this. You can do it matrices, but it's basically all going to get to the same place, right? So why don't I do this? Why don't I work with 2 of these equations at one time? Why don't I work with, I think the first and the third are the easiest to work with, because if I just look at the first and third, then I can just add straight down, can't I? Add these 2 equations together, and my t variable is eliminated right away, which is why I chose the first and third. And this tells me that negative 6s must equal negative 8, which means that s must be 4/3 positive, right? So I've got a good candidate right now. I know that for the first 2 equations, or sorry, the first and third equations, for those to be true, at the same time, I need at least the s to be 4/3. Now what? I can plug in 4/3 to where? Doesn't matter, actually, anywhere, right? Any of these. To get what t is? Let me go into the first one. Okay, so I'm going to take that, I'm going to substitute that back into the first one. 2 4/3 equals negative 1. And then, what? T minus 8/3 equals negative 1. Add to both sides. What do you get? T is 2/3? No, that doesn't seem right. Yeah. No. Yeah? 3/3. You're basically adding 8/3 to both sides right here. So that's negative 3/3. How did I do that? 5/3. What the? Tell you, my brain doesn't want to do arithmetic. Just does not want to do it. T is 5/3. So we good? We found a t and an s that work? Yeah? No, we didn't. We found a t and an s that made the first 2 true. Right? These are not supposed to intersect each other. We just said that. Show their skew, right? All we've done is found an s and t that make the first 2 equations true. But this s and t must also satisfy this middle one. Does it? You see what I'm saying? Everything we've been doing, we totally haven't even worked with that one. But we have this additional condition that must be true. So let's check this equation. Check this. Check it. Check. So is 3 times 5/3 minus, let's see, s was 4/3. Is that equal to 5? Nope, this is 5 minus 4/3 does not equal 5. Which means that that s and that t don't make all 3 equations true at the same time, which means that that's not a solution. But you have to have s and t be the same, be those 2 things, for these 2 to be the same. There's no other way you're going to get these 2 to be the same. So that means there's no way it can happen. Does that make sense? So what's our conclusion? They're not parallel, they're not orthogonal, and they don't intersect. So they're skew lines. That's quite a bit of work to show that 2 lines are skew, right? The hardest part being the intersect part, because that's a system of equations. Yes?
So the only way to figure out if they're skew is by process of elimination?
Yeah. There's not like a skew check, a simple skew check. Yeah, this is it. I suppose you could draw them. That'd be kind of hard to do in three-dimensional drawing, but we have a way. That's the thing. We do have a way. Oh, shit, we haven't even talked about planes yet. All right, planes. All ready, breath? We've got about 30 more minutes. The equation of a plane in three-dimensional space. We just saw that in order to define the vector equation of a line, right, we need a point on the line and a direction vector. Yeah? Or if someone gave us 2 points on the line, we could actually still do it, because we could always create the direction vector with the 2 points. So either one of those worked. And look, back in college algebra, it was the same thing. If someone gave you 2 points, you could find the slope, and then you could come up with, use that equation, right? Or if someone gave you the slope and an intercept, or slope and a point, you had a formula. So same thing, slope and point, or 2 points, this is kind of equivalent to that. Now we're focusing on defining a plane. To define a plane, we need 3 distinct points, and I showed you that earlier with my plane. If someone gives us 3 distinct points, right, then we can uniquely define one plane that goes through those 3 points. But there's something that's even more important for us to notice here. If I've got my 3 points here, let me rotate this around so you can see it. You want to see my 3 points living on my plane there clearly? Okay, if I were to connect vectors from the origin to those 3 points, right, then I would have 3 vectors, right? And then let's just look at the vectors connecting the points. Right, so you know what, the first 3 vectors, we didn't even really need those, so don't just wipe that out. You've got 3 points. Can you find the vector connecting this one to this one? Yes, right? Can you find the vector connecting this one to this one? Yes? So those vectors lie in that plane, don't they? So back on this picture, or on this, I have a vector here and a vector here. Both those vectors lie on this plane, don't they? And if I take those vectors and I cross them, I'm going to get a 3rd vector. And that vector should be perpendicular to the plane. Boy, that doesn't look perpendicular to me. There we go. That's a little better. That vector should be perpendicular to that plane, shouldn't it? Yes? So if I take some arbitrary plane sitting out here, do you agree that this vector that's perpendicular to the plane is perpendicular to all the vectors that ever could live in this plane? Yes? That vector right there is equivalent to the vector that's on the other side pointing in the other direction, right? So it doesn't matter which one I give you. Both of them are perpendicular to the plane. So what we're trying to get at here is, what is the bare minimum that you need to define a plane? We already said 3 points, right? 1, 2, 3, you define a plane. But maybe you don't even need that much. So what if I tell you this? I'm going to give you a point in space. Here it is. What's the only other thing I need to define the plane? A vector that's perpendicular to the plane. So if I now tell you, look, here's the point in space, and I tell you that vector is perpendicular to the plane, there is only one plane you can put up here. It's this one, right? It's that one right there. I couldn't put this one up because it's not perpendicular, right? Do you see that there's, with that point and that vector that I'm saying is perpendicular to the plane, there is a unique plane that goes through there. Do y'all see that? You see it? Okay, thank you. Plane that could possibly go through there. Yeah? So that's what we need to define a plane. That's all you need to define a plane, is a point on the plane and any what we call normal vector. A normal vector is any vector that is perpendicular to the plane. Any vector. Any, does not matter. And here is the formula for coming up with the equation of the plane. If x naught, y naught, z naught is any point on the plane, and this new vector, which we call the normal vector, which we're going to use n, is the vector ABC. If that is any normal vector to the plane, then the equation of the plane is given by this equation right here. What I do ask you to notice is that this is not a vector equation. Right? What we were just talking about with lines, right? We now have a new way of defining lines in 2 or 3-dimensional space, and it uses this very nice formula right here. But it is a vector equation. It's a vector formula. It involves vectors. With planes, what we're doing right now, our formula is not at the end of it all. It's an equation of a plane, and it doesn't have any vectors in it. Let's see any vector notation here? No? Angle brackets? No? Now, the A, the B, and the C, those numbers do come from a vector. It comes from the normal vector. The x naught, y naught, z naught is just a point on the plane. Understand? Now, we actually do have a way of drawing planes, though, with vectors. There is a vector equation of a plane. There is one. Would you like to see it? We won't see it till later, but would you like to see it? I'll show it to you. It looks like this. Check this out. I'll give 2 points bonus right now for the first take-home exam for someone who can explain to me, first one to volunteer to explain to me why that draws a plane. Anyone? Okay. How do you mean? What does that draw? A line, right? And it has that point in it, right? Okay. I'm still giving you an opportunity here. Yes, go ahead.
So that first part is the line, the S U.
This one right here?
That one will add another component to which you could draw a parallelogram.
Okay, yes, I think that's good. Okay, now I'm going to clean it up. This points to a point in 3-dimensional space, right? Let's say S is 0, all right? And this is TV. That will draw a line, won't it? So that's gone. That draws a line. Now, I want to let T be 0 and let S be anything. What's that going to draw? Another line through that point also. Now, let S and T be anything they want. So what would happen if I let maybe this be 1 and this be 1? I would go out on this line and out on this line and add them together, and I'd be somewhere out here, wouldn't I? But I would live within this flat space. And so I get basically all linear combinations of these two vectors, which would span the space. Yes, okay, you're shaking your head, that's a good thing. That's what's happening. Yeah, it's the span, right? The span of that would be a plane. So that's the way it would. But we're not going to do that yet. This is when we get into what are called parametric surfaces, and this is later when we're doing flux, and you've heard that before, flux and things like that. Okay, that's way later. That's going to be pretty challenging, actually. It's one of the hardest things in the class is coming up with parametric surfaces. But all right. I'm going to let you read through this. You're responsible for this part right here. I'll let you read that yourself. Find the equation of the plane through these 3 points. Remind me about that, okay? So I want to call on a different table now to see if someone can just tell me how we're going to do this. Because a lot of this is, when you look at these problems, it's you seeing, like knowing what you have to do. All right? So anyone want to volunteer from this table here to tell me what you're going to do, what your process is going to be?
First, start off by picking a point.
Okay.
On the plane,
Okay.
which could be any one of those.
Okay. You're going to pick one of these. Then what?
Find a normal vector to that point, or make that into a vector from 0 to that point, and then find a normal vector to that vector.
That's really close, but it's off and dangerously off, which is why it's good that we're talking about this. So the suggestion was to turn this into a vector, and then I guess use another one and turn that into a vector, and then cross them to make a normal?
No, just make a normal to the first one.
How would you make a normal vector to single vector? Okay, so let's go back to a drawing, okay? Anyone else at that table? You have 3 points. You're on the right, so pick 1 point.
Make a vector from one point to another.
Okay, so create a vector that goes from this point to this point, okay? Now what?
With that point,
You had it. Here, I've got it right here, look. Make another vector? Okay, so make another vector that goes from here to here. Cross those, and it'll give you a normal, won't it? That vector coming out will be perpendicular to the plane. That's correct. And then you use the formula. The formula requires that you have 2 things, a point on the plane and a normal vector. The point's already given, the normal vector you're going to create. Yes? So I need, in this point, or in this problem, I need 2 things. I need a point on the plane. Do I have that? Yeah, I have 3 of them, okay? I can pick any one of them I want. And I need a normal vector. That's what you need to define a plane. That's it. Do you have a normal vector? Not right now, right? You have to work for it a little bit. So let's create these vectors. Let's go from 1 to 14. Let's go to -2, -5, -1. And then here's 12, -3, 1. So those are just points. Now the vectors. So how about this vector? We'll call it V1. And this one right here, V2. So what's V1? V1 is -3, -7, -15. V2? Got it? What's V2? No, I'm asking if you can tell me what V2 is.
Oh, no, I thought you were asking right now.
No, I'm just asking if you can tell me what V2 is. Yes or no? Okay. 11, -5, -3. Anyone disagree? 13. Okay, maybe I didn't hear you. Sorry. 13, positive, negative? Negative. Okay, so everyone agrees with that? Now, cross them. So the normal vector is going to be the cross product of these 2 vectors. So this is where you have to cover up and do all that. Oh man, these numbers are big. Would be nice to have a calculator do our cross product right now, wouldn't it? So has anyone figured out how to do the cross product on their calculators? Anyone not have a TI in this class? Okay. All TI calculators that have graphing capability, you can write a program for, and there you can write a program to do a cross product for you. Just go Google it. You know, TI program for cross product, and it's very simple to put into your calculator. If you got the TI-86 or higher, it's already got cross product built in. Okay, so we go through this. Did you do it already? No? Okay, I saw you pull out the calculator. No one knows how to do cross product on their calculators? Doing it? Okay. I don't feel like doing it by hand. You know what we're supposed to do though, right? Okay, so I don't even think I can do cross. You work on it by hand while I try and cheat. I was going to go back and check it. Negative 15. I don't even think this is going to work. No, it did. Anybody get 16 for the first part? Yes? 16, negative 204, 92. That's it. That's your cross product. That is a vector that is sticking out of your plane and is orthogonal to the plane. And so the equation of the plane, we're ready to go with it. The equation is going to be A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. And those numbers are going to suck. What point are we going to use? We said we could use any of them, right? You want to use this one for our point? Okay. So the point I'm going to use is the point 1, 2, 14. So what's A, what's B, what's C? A is 16, B is negative 204, and C is 92. And if we just plug everything into that, we've got the equation. So 16 times x minus 1 minus 204 times y minus 2 plus 92 times z minus 14 equals 0. That's the equation right there. Now what you would need to do is distribute through and clean up, which I'll do right now. This is 16x minus 16 minus 204y plus 408 plus 92z minus, 9. What is it? 288 equals 0. And what we'll do is we'll get all our letters on one side and all of our constants on the other side, and we will have the equation of the plane. 16x minus 204y plus 92z equals... You'll notice I strike my z's, right? So you don't confuse them with 2's. What is it? Anyone got it? 1712? Any seconds on that? No? $896? Yeah. Let's look. 896? Okay, yeah, I think that negative 408, or that 408. Okay, so say again, what is this? 896? Okay, good. That should be it. How could we just, like, not check it, but feel better about it? Just make sure one of our points lives on that plane? Like, make sure 1, 2, 14 lives in here? So if you plug in 1 here, 2 here, and 14 here, you better get 896. If that checks out, then you should feel pretty good about it. But the other two should also live on this plane. Okay, does everyone know how to come up with the equation of a plane if someone gives you 3 points? Yeah? Okay, you got a point, put it away, who cares? There's your point. Then you create 2 vectors, you cross them, that's your normal, done. Now, the angle between 2 planes. If I have 2 planes sitting out here in 3-dimensional space, I should probably erase all that, huh? If you have 2 planes sitting in 3-dimensional space, and you want to know the angle between them, so here's a plane, here's another plane, right? Let's assume they intersect each other somewhere, and I want to know the angle between them. That means I'm talking about the smallest angle. I'm talking about this angle right here. Do y'all see what I'm talking about? Right in here. Right? I want to know what that angle is. Then how can we figure that out? What do you think? So I'm trying to get like a cross view of this. Does that kind of look like a cross view to you? Like we're trying to figure out what this angle is between these 2 planes? Well, check this out. Let me show you their normal vectors. There are their normal vectors sticking out. See their normal vectors? Now, normal vectors are just vectors, aren't they? They're just vectors. So I can move them around, can't I? Slide them around as long as I keep them pointing in the same direction. I'm going to move those normal vectors, get the other ones out, and I'm going to put them, orient them like that. Anybody see a similarity here? The angle between the normal vectors is the same as the angle between the planes. See, because isn't the direction of the perpendicular, this normal vector is perpendicular to the plane, right? So it's just 90 degrees more. So this normal is 90 degrees more than that plane. So all you're doing with the 2 normals is just adding 90 to whatever direction the plane's in. So the angle between the normals should be equivalent to the angle between the planes. Do you know how to find the angle between 2 vectors? Yeah, I hope so. Because we're going to do an example right now. Oh, by the way, 2 planes are parallel if and only if what? Their normals are parallel, right? So if you have the same normal vectors, right? These planes are parallel. The normal vectors, they don't have to be exactly the same, right? But they have to be scalar multiples. That would mean they're parallel. That's what this picture shows. Right? These 2 planes are parallel. Their normals point in the same direction. 2 planes are perpendicular if and only if their normals are orthogonal. Right? So 2 planes are going to hit at a perpendicular if the normals are orthogonal to each other. Okay. Let's see. See how you react to this. So let's clear your desk, take out a sheet of paper. Let's do this for a quiz. I want to see where everyone is. But I don't want you referring to anything except what's in your head right now. Just kind of want to see what's in there, what's not in there. I'll give you one thing, okay? This is a big gimme, but I'll give it to you. As a reminder, the angle between 2 vectors is given by this formula. You can use that. And you can use your calculator. So find the angle between these 2 planes. Some of you may get it, some of you may not. We'll see. Make sure you put your name on the sheet of paper. just your head. Does everyone have it written down? Give you another 10 seconds to write that down. Because I'm going to flip back in the notes to a page that might help you in case you're stuck. This might help you. Raise your hand if you feel like completely stuck right now. It's all right. Just, I need to see. I think what we'll do, since there's only about 2 minutes left, is I'll give anyone who's getting this the opportunity to turn it in for a bonus. Anyone else who doesn't feel comfortable with your answer, keep it. I'll just count this as a bonus. All right? But if you have it, just set it up here. Say one more minute. I'm going to show you that. That's why I'm going to stop in 1 minute. Okay, if you feel like you've got most of the work, you're just not able to get the last part of it, go ahead and turn it in so I can give you something for it. Anyone else? Anyone else? right, since we only have negative 30 seconds left, what is the thought process here? Just when you say find the angle between two planes, that means you have to find the angle between their normal vectors. All right? That's what I had just said in this note. Right here. I said the angle between two planes is the same as the angle between their normal vectors. So that means you need to define their normal vectors, right? So what is the normal vector of this plane? What is the normal vector of that plane? Well, I didn't specifically tell you how to look at an equation and see the normals, did I? Because I wanted to stress to you how easy it is to do. See, it seems, how many of you have found the normal vectors for these planes? A couple of you, right? The rest of you are like, how the hell am I going to find the normal vectors? Or just, I didn't know what to do at all? No? All it is, look at this right here. This is the general formula, right? Isn't A, B, C the normal vector? The components of the normal vector? Isn't that what we just said right there? N is the vector A, B, C is any normal vector? Okay? Notice what happens when you distribute through here, 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 and then do all the work. You finally get down to an equation that looks like this, right? D is some number, which is like here, it's the 5. Move to the other side. But notice that the number in front of x, y, and z are always going to be the direction numbers. So what is the direction of the normal vector for this plane? What is its direction? It's the vector 1, 1, 1. What is the direction for the normal vector of the second plane? 2, negative 4, 7, right? Now you plug into this formula. I have to change this to N1, N2, N1, N2. And that's something, that's a problem I could have asked you from last class or the class before. So you dot them, magnitudes of each. Here, cosine, I'm seeing 69.9 degrees. I think that a few people have turned that in. I don't know if it's right. I'll have to look, but 69.7. Does that seem easier now that you've seen it? Much easier? Okay. So the point is this. If somebody gives you the equation of a plane, is it hard or is it easy to find the direction of the normal? Easy, right? Very easy. Just look at the numbers. These don't matter for the direction of the normal. It's just the coefficients. Okay, everyone.
So does the angle have to be less than 90?
The angle will always be the shortest distance, or the shortest angle, because if the planes are opened up like further than 90, now we're talking about this angle. So the answer will be, and that has to do with the fact that the arc cosine will only spit back an angle, right? Well, 0 to 180, but you won't ever get, I don't think you'll ever get 180. Yes, because the smallest angle between two planes will always be acute, right? Like this. Like if that's the angle, this short one, right? If I go bigger, then now we're talking about this one. Yeah.
I thought that like this, because when you showed me that, I felt confused.
You felt confused?
Well, because I already knew that